So hello. Very nice to be here at Dubai. It's my very first time in Dubai. I really like it. I'm going to give a talk about choosing a database for your next project. So this is not so much specific to Python. You would probably do this for any kind of project that you intend to run. There are so many options nowadays. I just thought it might be a good idea to just go through a couple of options that you have. So first, a bit about myself. I'm Marc Lemburg. I have my own consultancy, choosijng. We do Python projects, mostly in the financial services space. I've also been around with Python for a very long time, so 1994. I think Travis has been around a bit longer than me. No? Anyway, I've been there since Python 1.1 or 1.2. I don't remember anymore. I'm also one of the core developers, so Unicode is basically my fault. And I've been very active in the Python community. So I was chair of the EuroPython Society that does the EuroPython conference in Europe. And I've also been on the board of the PSF. Right, so motivation about, why do you have to choose a database? So let's assume that you're building the next big thing, right? So next you have a startup, you want to create something new that's scalable. You don't know where you're heading yet when you start the startup, so you have to make some good decisions. Now, making good decisions is a bit harder than it was maybe 30 years ago. 30 years ago, you had maybe like 10 or 15 different databases to choose from. Nowadays, you have more than 800. I think the current number is around 850 or something. And if you want to go and shop for databases, a good place to go is this database of databases. And then you can have filters there to then pick your database. And I'm going to give you a few criteria to make that a bit more structured. So why do we have these many databases? As you all know, of course, the internet has basically completely blown up the space of scalability, and cloud is everywhere. So all these companies that you know, like Google, Facebook, LinkedIn, Uber, and so on, they had very specific needs for databases. They had to find databases that were very, very scalable, very capable of processing large amounts of data in very short time. And so these companies then looked at the databases that were out there and found that they could actually use none of these, because none of them had actually this kind of scale or this kind of capability what they were looking for. So what they did is they then started developing these databases by themselves, first in-house, and then a lot of them open sourced them. Nowadays, you also have quite a few startups that are smaller and are looking into the space as well, creating specific databases for certain niches. So that's why you end up with like 800 plus databases. Now, of course, when you do a new project, you could just go with the standard things that everyone knows, like MySQL, MariaDB, or Postgres. But if you do, then you might actually be losing a competitive edge. So you might actually not get the best that you can for your specific use case that you have. So it's better to look at this in a more structured way and then go to this database of databases, pick the right one, maybe do a proof of concept project to determine whether that choice that you made is actually good for you. And I'm going to go through a couple of steps here on how you can achieve this, how you can make a structured choice. So let's start with the typical data workload that you have. How many of you know OLTP and OLAP? Just a few. So OLTP basically means that you move in and you move in data into the database and out of the database very often. So you do like editing of, for example, user records in the database. That's a very kind of thing that you would do with online transactional processing. The second one, the OLAP one, is more about taking the data that's already in the database. The data doesn't change that much. So think about sales data, for example. You put it into the database, you keep it there forever. What you want to do is you want reporting to be fast. So you want to get data out of the database very quickly. And it doesn't change much, so you can optimize that process. Of course, in the ideal case, you would want both to be very performant and fast. But that is not really possible. So you have to make a choice there. The choice could, for example, also be that you use two databases, one for OLTP and then one for OLAP. So you can move the data out of the OLTP, let's say on a daily basis, into an OLAP database and then do the reporting. The next big thing to think about is the use cases that you have. So there are, of course, always a couple of things that you know already, but what's actually more challenging is thinking about the things that you don't know yet. Very often when you run a project, it happens that you start with a spec of the project, or you have an idea of what the project is supposed to be about, but then a few months into the project, you find that you might need a different twist on things, and you might have to make a few changes, and maybe suddenly you have to scale up very quickly. So it's thinking about these future developments that's very important, so that you don't create roadblocks for yourself in your project. And those are the unknowns. So one way to do this is you can have a look at different complexity dimensions in your use case. And I'm going to go through these. So first one is the schema complexity. So you have to think about, do you have a complex schema or do you have a simple schema? By the way, I see people taking pictures. I'm going to put the slides up online. You can follow me on LinkedIn and then you get the slides, so you don't have to take a picture of every slide I show. The simple schema are very simple applications like editing maybe a user database. That would be something that's very simple to put into a schema. Complex schemas come into play when you have to, for example, merge multiple systems that you have into one database. And so you have lots and lots of foreign keys in your tables. You might have lots of views in your database. So that would be a complex schema. Those are two things that you have to think about. And there's a third thing, which is called migrations. Migrations basically means that you change the schema over time. So you keep developing your schema, make changes to the schema, and so you have to make sure that the database you choose actually allows you to make these changes, ideally online, without taking the database offline. And there are a couple of possibilities in that space that you can use. The next two complexities are cardinal complexity and temporal complexity. So cardinal complexity essentially refers to how much data do you have in the database, how fast are you going to have data coming into the database, and so how quickly do you need to change, for example, your storage requirements. Temporal complexity is a bit different. This is mostly about figuring out how fast the data changes in your database. But it could also mean that you have an additional requirement, for example, for auditing purposes, that you have to know what did the data look like on a specific day in the past. So let's say you're in a bank and the auditor comes and wants to know what the data looks like on April 2nd. Who did what on your system on April 2nd? How did everything come to be to create some situation that required the auditor to come into your bank and do some checking? That's a very important requirement to have. If you don't have this in place, you're in trouble, right? So it's good to think about these things up front. Then, of course, next is query complexity. So ideally, you want everything to run as fast as possible. Everyone wants that, as we've seen with the fast-OSC Python and all these other projects. That's, of course, always a good thing to have. The more performance, the better. But you also have to think about the types of queries that you actually run against your database. So for example, are the queries going to have lots of joins? Are you going to have normalized tables in your database, or is it better to have a few denormalized tables? Denormalized means that you actually store data multiple times in multiple tables, which in normalized case you wouldn't do. So that's something that you have to think about. Some databases provide both in a very convenient way, or they actually help you with this. It's something to consider. In recent, let's say, years probably, or actually months, materialized views have become very, very popular. Only few databases provide this. So a materialized view is essentially, it's a table in the database that the database manages for you. So how many of you don't know what a view is? Oh, very few people. Okay, so a view essentially means that you run a select statement on your database, and you want this select statement, the output of the select statement, to work like a table would normally work in a database. And so you define this select statement as a view on the database. Now, when the database executes any queries against those views, it has to basically rerun that select statement every single time you access that view. Now, with materialized views, you can actually tell the database to materialize that view, so to actually create a table in the database that has the data, basically a duplication of the data that you already have in the database, but it's managed by the database, so it makes access a lot faster. So that's something that could make a difference in your use case. And then you have some special indexes that you need for full text search, for example. You have to look into those as well. So next is deployment complexity. So you have to think about how are you going to actually deploy your database? Is it going to live in the cloud? Is it going to be a managed database? Are you going to run it on Kubernetes? Are you going to run it on VMs, containers? You have to think of where the storage is being kept. This also goes back into the cardinality. So if you have lots and lots of data, you can't keep the data on a single machine anymore, right? So you have to distribute it somehow to some kind of S3 storage, for example. That's something to consider as well. And related to all of this, you also have to think about backups. Because at the end of the day, there might be a data center that gets set on fire for some reason, and then you cannot use that data anymore. You don't have access to the data anymore, and you probably want to continue running your business. And so you need to make sure that the backups are actually working, that you keep the data in multiple places, not just one. And this is resilience and disaster recovery. Those are very important as well. So one of the final thoughts here are the operational complexities that you have to think about. So like I said, manage, or do you want to self-host everything? Self-hosting may be an option for you if it's like a smaller setup that you're running and you want to have more flexibility. But ideally, if you're a small startup, I would always suggest to use a managed setup, because it's just so much easier to just focus on the stuff that you actually want to implement rather than running your database. If you do self-hosted, then it's very important to know how DevOps works for your database. So you have to look into the DevOps integrations that are available for your database. So for example, do you have helm charts for Kubernetes if you want to use Kubernetes for this? Or do you have Ansible scripts that you can use to basically set up your database? And then you also have to think about upgrades to the database code yourself. So let's say, like with Python, every year we get a new Python release. It's kind of similar for databases. Sometimes they fix security issues, sometimes they just add new features, so you might want to upgrade every now and then. You have to think about those upgrades because typically they require you to take down the database. Right, and the last thought on this decision making is actually some additional factors which are, I just put them on one slide here, but they're actually quite important as well. Because there's so many new databases out there, it's very important to look at how mature are these databases. So you have to check the code, you have to check on GitHub, for example, of how many check-ins these databases get. You have to make sure that the database is still around in 5 years' time, right? So for example, if you're, there are some databases out there that started really well, and lots of people put lots of code there, but then after 2 or 3 years, the people lost interest and they just moved on. And then if you bet on one of these databases, then you're basically stuck and you have to move out of that database into a different system, which may or may not be easy. So that's very important. It's also good to get support for a database. So let's say, I don't know, you want to use an open source database, let's say Postgres, right? Postgres is an open source system. It's free, you can download it, install it, run it, or you can just use a managed version of it. But how do you get support for it? So you have to figure out which companies provide support for you in case you get into trouble and you don't know how to fix those specific cases that you have there. So fortunately for Postgres, there are quite a few companies out there, for example, EDB, doing support, so you can get support contracts from them. But this situation is not the same for all the open source databases out there. Right, and because we are at a Python conference, of course, it also it's very important to think about how can I interface to the database from Python. So does it have a SQL Alchemy interface? Does it come with Django integration, for example? Depends a bit on what kind of stack you're using. So you have to look at those things as well. Now, fortunately, most databases nowadays do come with a Python interface because Python is pretty much used everywhere. So if you have a database that doesn't have a Python interface, then basically the chances that you're going to reach world domination are very low. So we're in a good position there. We were not in a good position like 20 years ago. So right. So that was enough talk about how to choose a database. So let's have a look at some of the databases out there for different use cases. So let's do some database testing. I'm going to go through a couple of these different options. I cannot possibly mention all of them, not even all different types of databases. It's just not enough time for that. Let's start with the general purpose ones. So these are ones where you don't really know exactly what you want. Maybe you start small. Maybe you want to later on then migrate to something else. These are the standard databases that you will always want to use. Postgres is my favorite. MySQL, MariaDB are great databases. Then you have the commercial ones, Oracle, SQL Server, IBM DB2. You usually get cloud versions of all of these. These are OLTP databases though, right? So if you want to do lots of analysis, then you're probably better off with something else. You can use in-memory databases. How many of you know SQLite? Great, quite a few, that's good. SQLite actually comes with Python, so there's nothing to install for you. Just import the module, it's there. You can use it. It's excellent. This is also a perfect way to get started with SQL in Python and to get to know the Python database API. A new database in that space is DuckDB. How many of you know DuckDB? Very, very few. So this is an excellent database, and I really recommend looking at it because it's rather new, but there's a lot of research going into that database, and all new developments in database science are going into that database. And it's really making great progress, and it has integrations with lots of other systems. For example, we heard about Arrow. It has an Arrow interface. It's a great database for doing OLAP. And it fills this kind of niche that we have in Python, where we just used to have SQLite for OLTP, and now we have DuckDB for doing the OLAP part as well. So if you want to do analysis, let's say you have, lots and lots of JSON files that you want to index somehow, it's very easy to just load everything into DuckDB, do the in-memory queries, which are extremely fast, and then get your results out fast. Another database which is commercial, though, is Exasol. How many of you know Exasol? No one. I figured, yeah. So Exasol, I just mentioned this because it's actually one of the fastest databases that we have right now. It's commercial, but it makes a lot of sense if you're using, for example, a different system. You find that a different system, the different database system that you're using is not fast enough, then you could put Exasol in between your applications and that backend database as a cache. And it will just speed up things tremendously for you. So next are two kinds of databases. One is called a data warehouse, and one is called data lake. Does any one of you know what a data warehouse is or a data lake is? Yeah, a few? Right, so data warehouse is essentially, you can think of it as a database system that is meant to store multiple databases from different systems. And ideally, you want to store everything into one kind of backend system. Of course, the ideal case would be that you actually then combine all these databases to build something, and that's why it's called warehouse, to build something that is interconnected. In reality, this usually never works, right? So you always get that requirement from a customer, and then you just have to tell them, okay, we could try it, but I can tell you 99% of the cases it's not going to work out. So it's better to just keep everything in one system, and then when you do need to access different data from different backend systems, you can then still just go into one backend system, and it's going to be faster than going to like 2 or 3 different databases. So the big ones that you have out there are, of course, Snowflake. You've probably heard of that one. Google has BigQuery for this. Azure has something for this. Amazon has Redshift. So these are databases that you would want to use if you have a need for storing lots of data, lots of different databases, and you want to make these things easily accessible. The nice thing about Redshift is that it's Postgres compatible, just like Greenplum. Greenplum is a database that specifically, it was built out of Postgres. So what they did is they took Postgres and then they replaced the storage layer with something else that makes it more scalable. And so you can use Greenplum as well, but Greenplum is mostly for if you want to run the database yourself. Redshift is always the better option if you want something managed. And then there's Teradata, which is kind of like probably the oldest data warehouse database there is. I guess they kind of started this whole thing. Used to be on-prem. You would actually have to buy a device for this. Now it's only fully managed cloud, so you can use that one as well. So the second thing is data lake. You've probably heard of that sometimes in marketing slides. A data lake is actually not a real database. It's well, how should I say this? Let's say you take S3 and all the data that gets generated in your company, so be it like sales data, be it like images or videos or audio files or whatever you have as data, you just throw it into S3. And then you put something on top that makes it queryable. So you might add some extra metadata, for example, and you can then query the metadata to get the data out again. This is what you call a data lake. So it's just a fancy word for, just this is my box where I put everything in, right? Athena is a great system for doing that if you're using S3. Athena can just, provide you with a SQL kind of interface to files that sit on S3. But you can also use other systems, like, for example, Apache Presto or Trino. Those are actually the same system. Trino is a fork of Presto. And then you can have different storage layers underneath. So you can use S3, for example, but you can also use other systems, like, for example, even Kafka or MongoDB as storage system. Or you can use Data Lake. Data Lake is basically a storage engine as well that has, like what you typically have in relation databases is an ACID compliant one, so it has transactions. So these are options that you have for data lakes if you want to store everything in one place. Now, let's say you have a startup that wants to provide a service, and the service is not just local, but it's worldwide. So you need to think about how can you store everything worldwide and make it easily accessible. So you need something that's distributed. So not just storing data in one place, but it's storing it in lots of data centers around the world. Then you need a distributed system for this. And a very good system is Yugabyte DB, which is also fairly new. It's Postgres compatible. There's also CockroachDB, which is also Postgres compatible. But I would prefer Yugabyte. So if you want to have a look at these things, then Yugabyte is probably a good choice. If you're more into MySQL compatibility, then Single Store would be a good contender for this. If you have lots of data that is like time series data, it's log data, then ClickHouse is an excellent option. ClickHouse was developed by Yandex, which is kind of like the Russian Google, and they used it for doing something like Google Analytics. So it's extremely fast if you have lots of data to intake and you want to do clickstream analysis. And then, of course, you have Exasol again, which basically does something similar, but it stores everything in RAM, puts all the RAM on a cluster, and so it's extremely fast in getting the data out again. Right, those were more the traditional kind of databases. They typically have SQL kind of access to the databases. Now I'm going to talk about document databases. So what you want to do is you want to store text data in the database, or you want to store structured JSON data, for example, in the database. Now, most of you will probably know Elasticsearch. Maybe if you know OpenSearch as well. OpenSearch is a fork of Elasticsearch that still comes under the Apache license. So if you do something that you want to maybe distribute as part of the product or a service that you want to provide to customers, then OpenSearch is probably the better option. Or you just team up with Elasticsearch and then, or Elastic, the company behind it, and then you can use Elasticsearch as well. Apache Cassandra is a very nice and new system, and also provides SQL access to the data that you have in the database. Unlike Elasticsearch and OpenSearch, they have a specific, a custom kind of query language that they're using. And then, of course, you have MongoDB. Everyone knows MongoDB, right? CouchDB is interesting because if you, let's say, you want to build something that uses mobile apps and you need to do synchronization, then if you've ever worked with synchronization, then, sorry, there's this fly here, so if you've ever worked with synchronization, it's very difficult to get synchronization right. And CouchDB does an excellent job in doing that for you. So whenever your device comes online again, it will automatically sync with your database, the backend system. So very nice database. Next category, time series. So you have lots and lots of log data coming in, you have lots of event data coming in, you want to store that somewhere. A very popular one is InfluxDB for this. A very new one is Apache Druid. Apache Druid is a lot faster than InfluxDB. You can also combine things, like for example, use CrateDB, and then you get, document search, and you get time series search in one database. Or you can just use your Postgres database that you have, and you put the timescale DB extension on top of it, and you get time series in Postgres. If you have a requirement, like I mentioned with the auditing, so you have to know when something changes in your database, and you have to know and maybe show your auditors what happened when in the database, then you need to think about immutable databases. So a database where you cannot change the data anymore once it's in the database. And there's a very nice database called ImmoDB, which is, it's append-only, it's immutable, and it's actually tamper-proof. They're using cryptographic algorithms in there to make sure that the data doesn't change. And that's just fantastic for auditing. Right, and I'm coming close to the end now. Machine learning and databases. Machine learning is all the hype right now, right, with AI and everything. Of course, you need to store the data for your machine learning model somewhere, and you need to often extract the data that you need to, in order to train the models from databases that you have. Now, of course, pulling all this data out of the database first, and then sending it through your machine learning workflows that you have, is very inefficient, because it's typically lots of data that you have to, move through the system. So wouldn't it be better to just have the machine learning sit right in the database kernel? And that's exactly what a couple of databases do. And if they don't, then there is this Madlib package that you can use and you can install, for example, in Postgres. And you can actually run your machine learning models using Python directly in the database kernel. Other databases do that indirectly. They provide Python UDFs, so user-defined functions, so you can do the same, but it's more complex to do. Or you can even take another approach, and then, let's say you have engineers that don't know Python, but they do know SQL, and they want to do machine learning as well. Then you can extend SQL with certain statements and functions to make machine learning possible, and you put this MindsDB proxy in between your database and the application. And then you can have your SQL engineers who know you want to do machine learning as well, use machine learning. That's a very nice approach that they have. So I've talked a bit about various different types of databases. I've not even covered, probably just the tip of the iceberg. I've not talked about key value storages, for example, not talked about Redis or anything like that. There are databases that actually work on GPUs. So let's say you want to visualize huge data sets and you want to have them interactive, which is probably also something that you need for this metaverse thing. You need to have access very, very quickly to the database, and you need to process the data very quickly. So GPUs is one way to do it. Of course, you need to have a sizable budget in order to make that happen, right? And lots of, very capable GPUs, lots of RAM to make that happen. Other use cases are geodatabases. So let's say you want to find the next available Uber in a certain, area. Then, of course, you want to query the data based on geo-coordinates, right? And then, maybe areas or distances. That's what geodatabases are for. If you use Postgres, there's a very nice extension for Postgres for this, so you can do that. But there are also specialized databases. Graph databases, something very important. So let's say you want to store relations between different entities, different interconnections between entities, yeah? Then you need to put that data into your database. You then maybe want to do graph algorithms on this data without actually having to code the algorithm. You just tell the database, okay, I want, let's say, minimal spanning tree or so of a couple of nodes that you have in the data. And they will then basically just provide that for you. So you get databases for that as well. If you're into machine learning, then you will probably want something where you can store vectors. So to store your embeddings, for example, in a database, and to make those the models that you have available to your developers in a way that they can actually, recreate, like what we had with the VNs before, recreate the same kind of environment that a developers use to run a certain mechanism or a certain algorithm. This is something that's is still very much in development. It's basically trying to do version control for models, and vector databases are a great great way of actually making that happen. Something that's rather new are strongly typed databases. I can't really tell you what people will want to use those for, because database, of course, they have types, but they typically don't have structure types, right? So the strongly typed databases add a way to databases to basically implement structures. So you can say, okay, I want this kind of, let's say you have a JSON file, and a JSON file has or should have a particular structure. You can put that struct into the database will then do the validation and everything for you, and then make sure that everything is strongly typed. So there's database obviously called typedDB, which then implements this. And there are many more. So I've given you a quick overview of 30 plus databases. I hope this was useful. Lots of great options out there, but there are also, lots of questions to be answered, lots of things that you have to, look into to find the best pick. So main takeaway from the talk is, never stop to learn, always try new things. There might be something around the corner which is exactly what you need. You just have to find it. Thank you.
Thank you, Marc-Andre. That was a fantastic talk, and I found it very useful. My only comment is that I would say I've used MongoDB in production, and never again. Anyway, that's a terrible slur. Does anyone have any questions?
Hi, thank you for that talk. So this will be a slightly long question. I have two parts to it, one software-based and one's hardware. Starting with the talk, I've been reading a lot on a lot of blogs regarding databases, and I think what you covered up sums up much more than what I've read in the past year. So thank you for this lovely sum up. First question, the strong type, the last bit that you spoke about, example SQLite also has types but doesn't enforce them.
Right.
So what do you mean by the strong type? That's
okay. So of course databases have types, right? So you say, okay, this is a string, this is a float, this is like, I don't know, a blob maybe. But those are basic types. Now let's say you have a field in a database that's supposed to be have structured fields within that field in the database. So like a C struct, yeah? Then you can, in those databases, you can say, okay, this field is going to have subfields or attributes, let's call them, that are built according to a certain, strongly typed structure. So it's like putting a C struct into a field of a database, and the database then takes care of all the validation and type checking.
And enforces it.
Yes, and enforces it.
Okay. Second question. This is slightly off topic, but related to data. As we move into a 5G world, and in India 5G was launched recently, and a lot of autonomous vehicles and all this is coming in the future. So the amount of data we produce as a species is only going to really grow. So my question is that today data is concentrated, or at least data centers are concentrated with few brands in the world,
right.
Say AWS, Google, etc. But there's this new buzzword that I keep seeing on LinkedIn, edge computing. It keeps
right.
showing up. So do you see a future for say McDonald's planting a AI solution in the future 10 years later and wanting a data center that is not necessarily on the cloud but closer to the franchisees of.
I definitely see a use case there because obviously it takes time to get the data from the data centers onto, let's say, a mobile phone, right? So it makes sense to, for example, store part of the data that you need on your local phone. So that would be an HDB kind of thing, right? So let's say Google Maps, right? You can download a certain area of Google Maps on your phone, which is basically a database that you're creating there on your phone, right? So you have the data locally on your phone, and it works even without the connection to the main data center, right? And that's exactly what this edge computing does. It moves the compute and the storage, part of the storage, to the mobile devices. And that's certainly something that's going to be very important in the next couple of years.
So you would say that for entrepreneurs looking at this kind of a business model in the future, there is scope for starting data centers that support edge computing to local businesses rather than just the big ones coming and taking over also the edge computing data centers in and around?
So you have to be careful there a bit. I mean, with edge computing basically means that you move the compute more closer to the users, right? I would never move the data from the data centers to the edges. I would always just replicate data from the data centers to the edges so that you get faster access. For example, what CloudFront does, right? So basically you have a CDN, and the CDN then moves the data from your web servers closer to the end users, so to the exit nodes, let's call them, that are closer to wherever the user is, so that you get faster access to the files, right? You can do the same with data. And Amazon actually provides this kind of service as a, I don't know what it's called. It's you can actually distribute the data closer to your end users.
Got it. Thank you.
There's 3 questions for the price of 1. Do we have any more questions? Thank you. Question at the back here. Oh, we have a couple of questions. Who's going to get the mic first? Over here on the right.
Hi. Nice talk, certainly.
Thank you.
I used to work for Teradata, so it was nice to see Teradata on the slide, which is slowly fading away. So I'm working on an internal project to migrate from Oracle to Postgres.
Mm-hmm.
I know you mentioned that Postgres is your favorite database. So I don't know, you don't have to, but what would be the main benefits of using Postgres as opposed to one of these other fancy new databases?
So, I mean, Postgres is it's a universal database, right? And the nice thing about Postgres is that you can extend it in various ways. So you can add extensions to Postgres to make it do certain things that are normally not in Postgres. So that's an excellent way of experimenting with new database technology. The one thing about Postgres that doesn't work well is scalability. So if you have lots of data and you want to put lots of data into your Postgres database, then running it on a cluster doesn't really work. So you have to go to a different system then. For example, Greenplum, yeah? Or you have to use, maybe Redshift as an alternative for that. If you know that your database is going to, be within certain bounds, it's not going to grow too much. Postgres is the perfect choice because it doesn't prevent you from, extending your the work that you're doing in certain areas. There are always ways of adding new functionality to it. Now, because you said you're moving from Oracle to Postgres, that's actually something that's very common nowadays because people want to get out of the lock-in of Oracle. They want to reduce the licensing costs. And even though the migration is, of course, costly because it typically means that you also have to, transform the stored procedures that you have in Oracle into PLSQL, which is the stored procedure language in Postgres, I think it pays off, within, let's say, 5 years or so. So it makes a lot of sense to do that. And after those 5 years, you're basically, outside the lock-in that you have. You're open to move into other spaces as well, and you can also get the scalability if you want to by then moving either to Greenplum or moving to Redshift.
Thank you.
I think we have time for one more question, and we have someone at the back ready to go.
Yeah.
Hello, thank you for this great talk. My question is, with this ever-growing privacy concerns, people are more concerned about how their data is stored and by whom. And in parallel, and due to that, there has been growing research into things like federated learning, homomorphic encryption. Are you aware of any active research in either academically or in industry about, for example, centralized or decentralized database systems that could allow such computation on a decentralized way and in a privacy-preserving way?
That's a very good question. So I didn't understand it fully, but I guess the question is mostly about what are the consequences of moving data out of a central kind of managed database into a cluster distributed with all these privacy concerns going on, right? And so let's say you have a leak somewhere. Of course, if you store the data multiple times throughout the world, then the exposure is also, amplified. I'm not really sure whether there is any research on this. I do know that a lot of companies are actually masking data in the database, so they're not actually storing the real data in the database, but instead they're storing either masked data, so it means that you replace certain parts of the personal identifier data with, let's say, placeholders, or what they do is some databases also encrypt the data, right? Of course, when you encrypt the data, you often lose the searchability. So it's a trade-off that you have to do there. So if you want to prevent or make it less likely that that data gets lost or gets leaked for some reason, then it's usually best to use one of those strategies. But it doesn't always work. So for example, if you need to search for private for PII data, then you cannot encrypt it, right? Or you have to create an index that is actually where the index is being built on the unencrypted data, but then you store the actual data in an encrypted form in the database, and then you just decrypt in your application when you get it out. That might be a way to do it. So I don't know. This is, I guess, ongoing research. All right, thank you very much.
Thank you, Marc-André. Let's thank him once again for his talk. Thank you.